Okay, so when we talk about the colloidal precipitates, okay, so we know that when we talk about colloid, so colloid particles always refer to the positive and negative charge, just like what we see in the previous figure, the silver chloride formation. Okay, so by the time the colloidal suspension form, it will coagulate and agglomerate. Okay, so when we talk about coagulation and agglomeration, from these suspended colloidal particles, it will unite to each other in order to form a larger filtrable particles. Okay, so what you can see that coagulation and agglomeration is the next process after the colloidal become after the colloid become colloidal suspension. Okay, so it can be synchronized by adding an electrolyte to the medium, heating and stirring. So in order for you to enhance the quality of the precipitates, you can also heat the colloidal suspension or stirring the colloidal suspension, and suddenly it will become the larger filterable particles. Okay. Okay, other than that, we also have peptization. Okay, this what we call as a redissolution of coagulated colloids by washing and removing inert electrolyte. So for the peptization, we always refer the coagulated colloids, okay, as the high impurity, as the high quality of precipitate. Sorry, as the high quality of precipitate, okay, by washing and removing the inert electrolyte. Okay, so here is the peptidization. What is peptidization? Is a procedure where the precipitate is washed and filtered, but most of the precipitate reverts to the colloidal form because supporting electrolyte is gone. So basically, when we do peptidization, this is the process where we will wash our precipitate to remove the impurity and also to remove the excess ion or electrolyte that might be attached on the precipitate. Okay, so this is what we want to uh, this is why we want to wash our precipitate, because we don't want the peptidization to be occurred, or we don't want the precipitate to return back into the solution. Okay, we want it to become a precipitate. Okay, next, cooling the system with an ice water bath minimize the loss of precipitate due to this solution. Okay, so when we do a peptidization, it means that we try to cool the precipitate in order to minimize, okay, to minimize the dissolution. Okay. Okay, for the formula that involved in the precipitation technique is what we call as saturation. Okay, saturation equals to Q minus S. Okay, so when we talk about Q is the solute concentration, whereas S is the solute solubility. Okay, so in this formula also we can calculate also the relative supersaturation, which is Q minus S divided to S. Okay, so what did you expect when you calculate the saturation or the Q value? Okay, so you should know that when you have a um, Q value low, okay, so you can get the very best results. Okay, and when you have a very low Q, you will have a very relatively large, okay, of S value. So when this happen, you can see when Q increase and S decrease, so you will get a high supersaturation. So when we have a high supersaturation, it means that you will produce a fine particles. Okay, so when you will have the fine particles, it means that it has a potential to return into the solution and become colloid. Okay, not a precipitate. Okay, so when we talk about when Q is decreased and S or the solid stability is very high, so we can estimate that it is consists of low supersaturation and the large particle will be formed. Okay, so this is the analytical precipitation from hot solution. You can see when you have a very hot solution, it means that you increase the temperature and at the same time you also increase the solubility. When you have high solubility value, so you will decrease the supersaturation. So when you have a very low supersaturation, you will increase the particle size. Okay. So next is from dilute solution. For the from the dilute solution, you will see here the molar concentration of mixed reagent low. Okay, so we can have a very good analysis. Okay, when we have a very dilute solution. And another point is that when you add the precipitant slow, okay, so slow and with a stirring, you will also produce the low Q. So here you can see when you have a lower pH, which is a more acidic, the precipitate become more soluble. Okay, so when you have a precipitate that more soluble, it will decrease the precipitation rate. Okay, so when we talk about precipitation rate, is actually the precipitate concentration divide to time. Okay, so when we talk about rate, it always refer to the time. Okay, so it means that you will get the precipitate in a very short period of time. Next is digestion. So in order for you to understand the digestion always improve the organization of atoms within crystalline nuclei. So when we have different kinds of parameters, okay, so you will always alert on these different kinds of terms that you can use for to get a high quality of precipitate. So the first one is use a dilute solution. So from this dilute solution, you can decrease the Q value. Next is add precipitating agent slowly. So you can see when the Q value is low, so you can get a very good precipitate. Okay. Next is stirring during the above addition. So by the time you stir the mixture, it also can keep the Q value low. Next is use hot solution. So when you use hot solution, you increase the temperature and at the same time you also increase the solubility. Next is adjust the pH. When you adjust the pH, for instance, at lower pH value in the acidic reagent, it also increase the solubility. Next is add precipitating agent with excess amount. So here we can see when you have a large amount of precipitating agent, it will help you to get uh, the precipitate, okay, completely react with the uh, ion or our analyte. Okay, when we talk about co-precipitation, when we refer to co-precipitation, we always refer to the impurities in precipitates. Okay, so this is the method that commonly happen, and it is not easy to be removed. Okay, because we cannot control. Sometimes we cannot control these impurities. Okay, so what is co-precipitation? Co-precipitation is a process where the impurity is precipitated along with the desired precipitate. For instance, barium sulfate, hydrous oxides compound. Okay, so basically, when we have the what we call as impurities, okay, so it means that we don't want this compound to be in our precipitate. Okay, so basically, when the soluble compounds uh, easily soluble in the water, so it will easily to be trapped in the precipitate. So for the impurities, we have four types of co-precipitation. The first one is surface adsorption, which is occurred on the surface only. Second one is occlusion. This is what we call as pockets of impurities that are trapped inside the rapidly growing crystal. And the third one is inclusion. The impurities ion replace an ion in the crystal lattice. And the fourth one is the mechanical entrapment. So this entrapment happen crystal lie close together with during growth. Okay, so this is a more physical problem. Okay, so you can see when you want to minimize the co-precipitation, you need to be careful through washing. Okay, especially washing. So here we can have different types or different methods on how to minimize the impurity. Okay, the first one is reprecipitation. It means that you wash or um, you dissolve your precipitate. Okay, you dissolve again your precipitate, and after that try to produce the precipitate again. Okay, by washing away the mother liquor. Okay. Okay, so next is dry the solid. So basically, when we dry the solid, okay, at temperature about 120 degrees, it can be varied. Okay, different analytes will require a different temperature, so it will depends. Okay. Next is precipitate in the presence of electrolyte. So here it will always refer to the Coulombic repulsion. Okay, is diminished. Okay, so when we talk about the precipitation in the presence of electrolyte, so we always refer to the Coulombic repulsion. Okay, and the last one is digestion. Digestion occurred when you increase the temperature, so you will also increase the collision energy. So from here you can see when the collision energy increase between atoms, so you can see that the Coulombic repulsion is diminished and you can form a larger particles. Okay. Okay, so for the gravimetric analysis, we always refer to the calculation. Any application in analytical chemistry, we will always use calculation to solve a problem. Okay, so basically, when we talk about gravimetric analysis, calculation, it does require you to understand what is the chemical reaction happen, what is the stoichiometry. You need to balance the chemical reaction first, and you need to know what is the precipitate. That is very common information that you need to know before you can solve any problems that might relate to the gravimetric analysis calculation. So for example, the determination of silver or chloride ion by the formation of silver chloride. So here you can see that Ag plus, okay, the silver ion plus with chloride ion will produce silver chloride as a precipitate. Okay, so as you know that this silver chloride will have a KSP value. Okay, so this is the constant for the solubility product. Okay, so the value is 1.8 times 10 to the power of minus 10. So this KSP value is fixed, so you don't have to calculate, because this value is already um, it's already fixed and it will not change. The only things that might be changed is the concentration. Okay, so here when we talk about gravimetric factor, so this is the part, very important part, that you need to know that gravimetric factor is exists. Okay, so when we have different kinds of precipitate, okay, and by the time we want to compare the precipitate with a different compound, okay, we need this gravimetric factor. Okay, so what is gravimetric factor? Gravimetric factor is the weight of analyte per unit weight of precipitate. So you must know what is your analyte, you must know what is your precipitate. Okay, so basically the analyte is the chemical that we are looking for, or I mean the compound that we are looking for. The precipitate is the solid, the solid form. Okay, the solid form that produced after chemical reaction happen. So this is the formula that involved in calculating the gravimetric factor. So here A is the moles of analytes and B is the moles of precipitate. Okay, GF is the gravimetric factor. So you can see when you have this value, the gravimetric factor, you must times between the ratio of moles of analytes towards moles of precipitate times with the molecular weight of analytes divide to molecular weight of precipitate. Okay, so in order for you to determine the percent of analyte, you must know that weight of analyte divide weight of sample times 100%. Okay, and this is a very common formula that you will use in any calculation that require you to calculate what is the percentage of your analytes in the precipitate. And you must know also that we have another formula for gravimetric factor, which is mass of the analyte divide mass of the precipitate. Okay, so here you can see also the percent weight per weight. Okay, weight per weight of analyte must be weight precipitate, okay, times with the gravimetric factor divide with the weight sample. Okay, so this is what we call as a percent weight per weight. Okay, so for this part, this is an example, okay, for you to calculate your analytes from the precipitate that form. Okay, so in this case, in this example, you can see that your analyte is sodium chloride and your precipitate is silver chloride. So what I want to show here is that your ion, the most important ion in this between this analyte and precipitate is actually chloride ion. So when you look at the chloride ion in analytes and precipitate, you can see that the ratio is 1 to 1. Okay, when you can see very clear that the ratio is 1 to 1. That's why in the ratio of um, mole of analyte towards mole of precipitate is 1 to 1 in here. Okay, so by the time you want to calculate the ratio mass of analyte towards the precipitate, or we call as the gravimetric factor, you can see that you will use the same formula, okay, and then you just include the molecular weight of each compound, okay, and after that you can easily get the gravimetric factor, okay. For example 2, we have analyte is 2K2HPO4, and the precipitate is the magnesium 2P2O7. Okay, what is the similar elements that might contain in analyte and precipitate? Of course, the phosphorus. Okay, so here you can see the similar thing is the phosphorus. So that's why in your analyte, okay, you can see in your analyte the ratio is 2 and the precipitate is 1. Okay, so by the time you calculate the gravimetric factor, you can easily use the same formula, and you need to know the molecular weight for different compound for your analytes and the precipitate. Okay, example 3. So in this example, okay, you can see we have a analyte, okay, we have analyte which is a ratio 1 and precipitate is ratio 3. Okay, so you can see very clear that we have what we have here is that the ratio between the analytes and the precipitate is 1/3. Okay, so here you can see the gravimetric factor is by using the same formula, and you must know the molecular weight, and you can get easily to calculate the gravimetric factor. Okay, next is for the volatilization gravimetry. So in this technique, we always refer to the something that or the common analyte is like water or carbon dioxide. So basically, water is when we heat up and it will become a vapor. And for the carbon dioxide, basically like a combustion process, it will like a combustion process for fuel. So we can easily get the carbon dioxide, okay, as the product. Okay, for water, okay, for water we have two types of method. The first one is direct method and the second one is indirect method. For the direct method, the water vapor is collected, okay, by using different kinds of solid desiccants. Solid desiccants is the something that chemical or a solvent that have a high quality of to absorb water. Okay, so that is what we call as desiccants, and its mass is determined by from the mass gain of desiccants. Okay, so in such a way for this what we call as desiccant. So desiccant is the chemical or the powder that we can use, okay, uh, to calculate the different mass from initial to the final stage. Okay, so the mass different mass equals to mass final of desiccant minus the initial mass of desiccant. Okay, so you can easily get the mass of water, okay, from this direct method. Next is the indirect method. So from this indirect method, we For instance, like we do heating, okay, we do heating and we can easily determine how much the water are lost from the sample. Okay, so we can determine, also can determine this by using this heating process. Okay, for the particulate gravimetry, we have two approach. The first one is filtration. Okay, for the filtration, we use the solid particulates. Okay, the solid particulates are separated from their gas, liquid, or solid matrix. Okay, and for the second one is extraction. Okay, from this particulate gravimetry, you can extract the sample from its matrix with a suitable solvent such as liquid extraction. Okay, this is what we call as kinds of extraction. Okay. Okay, so for the application of particulate gravimetry, we can use is for the microbiological testing of water. Okay, that is one big area that nowadays has been used. Like they want to detect the E. coli in the sample, in the water sample. Okay, next is determination of suspended solid in river water. So basically, for the water quality parameters, it does require how much the suspended solid that might be contained in the water body. So they can use from the data, okay, I mean from the gravimetry method to determine how much is the total solid suspended in the water body. Okay. The third application is total airborne particulates by using high volume air sampler. Okay, so this is just for the sampling technique. Okay. Next is grain size distribution for sediments and soil. Okay, so you can see that by using different kinds of filtration, okay, and also like the sieve set, just like what you seen here. This is what we call as a sieve set. Okay, we can differentiate, okay, the particles according to different size. Okay.